Evening. I'm Spot On Weather meteorologist Matthew Euler. Welcome to my latest training video. And in today's training video, we're going to examine pressure systems. We're going to talk about high and low pressure systems and what they mean for your weather. And then we're also going to talk about the different types of high pressure systems and as well as low pressure systems, the different types. Let's get right into today's training. All right, so let's start things off and talk about high pressure. And what is high pressure? Basically, we talk about an area of higher pressure. It's an area of higher pressure surrounded by lower pressure all around it. It's known as an anticyclone or a dome of high pressure. And you can clearly see that over here in the upper right on this graphic. Notice how you have this dome type appearance or a dome shape when we're talking about high pressure. In the northern hemisphere, the wind generally is going to blow in a clockwise manner around high pressure systems. So here's your high pressure represented by this H, the letter H. That's the center of your high pressure. And the wind is generally going to blow around this high pressure system in the northern hemisphere in a clockwise manner. Generally from the north on the eastern side of the high, generally from the east when you're south of the center of the high pressure system. And on the west side of the high pressure system, the winds are going to veer around to the south. And if you're located north of the high pressure system, the winds are generally going to be from the west. Just like water flowing downhill, the flow also is going to be directed outward and away from the high pressure center. All right, so when we look at surface high pressure, we generally have a weaker surface wind near the center due to a weaker pressure gradient. And what a pressure gradient really is it's just a change in the pressure, the barometric pressure, over a specified distance. It's labeled on the surface weather maps as a blue H. So if you see the nightly weathermen or meteorologist on there doing the weather segment on your local news, you'll notice the blue H. That denotes high pressure. And it forms when we get this upper level convergence of air, wind coming together high above the ground. So air is coming together aloft. And then as the air meets, it generally results, and I'll go ahead and draw this out so hopefully you better understand this. Whenever you have the air converging, eventually in the upper levels, the air is going to sink in the vertical here, down the center of the high pressure system. And once you get to the surface, you get more of that low level divergence now. So upper level convergence, air coming together aloft, over low level divergence where the air is spreading apart at the surface right at this location. And that's generally what happens with high pressure systems. And whenever you have this sinking air motion, by the way, drawn by this arrow here, you got this arrow acting downward as the air sinks, it's going to add surface pressure generally at the point beneath where the air is sinking. All right, so this, by the way, when you have upper level converging air aloft or above the surface over lower level diverging air at the surface, that is something that's known as the damper effect. Now that you have an idea what high pressure is, let's take a look and examine the various high pressure types. We'll start first, we'll take a look at warm core high pressure, then we'll look at a cold core high pressure, the semi-permanent high pressure, and then finally we'll take a look at the migratory type of high pressure. Starting with warm core high pressure, it's generally going to, the warm core, whenever I say warm core, any type of atmospheric system, we're basically delineating that the air is the warmest at the center of the pressure system itself. The warm core high pressure is going to have the warmest temperatures towards the center of it. It's very common to see a warm core high pressure system in the subtropical oceans, generally with an average position of about 30 degrees, both north latitude here in the northern hemisphere. You'll see this warm core high pressure system there. You'll also see it at 30 degrees south latitude in the southern hemisphere. This formation, again, is a result of large areas of sinking warm, dry air, and its vertical structure generally shows higher heights above the surface position, which makes a lot of sense. You get higher heights, which are going to be associated with warmer temperatures, a warm core above the surface position of the high. The axis of this high pressure system from the surface aloft is going to stack back slightly towards the equator or the warmer air. Again, here's your globe on the right, and just showing you generally at 30 degrees north latitude and 30 degrees south latitude, we have this warm core high pressure system. And in the northern hemisphere here, that's generally known as the Bermuda High, which is a very, very significant feature when it comes to the East Coast summers. Now let's talk about cold core high pressure. These generally form in the polar regions. The formation occurs over land masses and persists with convergence aloft. Remember that air coming together aloft, accompanied by intense surface cooling, which makes a lot of sense. In the polar regions, you generally have a snow-covered landscape in those polar areas. Cold air is going to be very dense, so it remains closest to the ground, and the high pressure does not extend to great heights for cold core highs. In the upper levels, we typically see a weakening with height, and in some cases, the circulation actually reverses from an anticyclonic or clockwise rotation of air to cyclonic. So you can actually get, if you look over here on the right-hand diagram, so you have your high pressure at the surface, the cold core high. You notice how it acts like a shallow dome. The coldest air is going to be concentrated at the surface. Go ahead and put this back here. So you got the coldest air is going to be concentrated towards the surface because that air is so dense. Your center of your surface high pressure is here. Look at this dome effect. Now these are your heights, how they change with as you go up in the atmosphere. So you notice how we have like this dome-like structure all the way up through 5,000 feet. It's a very shallow dome of high pressure. But then as you get further aloft, up at the higher levels, you sometimes get a reversal where you get a trough or an area of lower heights aloft above this cold core high at the surface. It generally tends to strengthen in the wintertime and will dissipate or weaken during the summer. The semi-permanent high pressure system now, these are high pressure systems, they're warm core in nature, they tend to persist at particular latitude throughout the year. And we kind of hit on this with the first type. We talked about the warm core high pressure. And I gave an example of that as the Bermuda High in the Atlantic Ocean. And the Bermuda High is not only a warm core high pressure system, but it's also semi-permanent. Semi-permanent meaning that it just generally stays the same latitude in the same region throughout the whole entire year. Now, the Bermuda High does shift with the seasons. In the winter, that Bermuda High is going to move further south in the northern hemisphere towards the equator as your jet stream of storm track shifts south. In the summer, the Bermuda High is generally going to expand poleward or to the north in the northern hemisphere, and that's going to result in very muggy conditions on the backside of that Bermuda High across the east coast of the United States. Very muggy air masses throughout the summer. And here is the breakdown. I kind of already covered this. In the northern hemisphere, this Bermuda High, or this high pressure system that's warm core and semi-permanent, it's generally going to slightly shift northward in summer and further south equatorward in the winter in the northern hemisphere. The Bermuda High, by the way, is centered around 40 degrees north latitude in summer. Like I said, it moves further north in the summer, and it's going to shift down to about 20 degrees north latitude in the wintertime, with your storm track shifting much further south. So over here on the right, I'm showing you the average position of the Bermuda High in the northern hemisphere, this warm core semi-permanent feature, around 40 degrees north in the summer. And on the right-hand side here, I show you how it shifts to 20 degrees latitude in the wintertime. What about migratory high pressure systems? This is our last type we'll talk about for high pressure. They originate in the polar regions. They're generally cold core. Now, when I say cold core with these migratory highs, that means the coldest air is going to be at the center of this high pressure. A portion of this migratory high is going to break off. It begins to move with the upper level winds. The jet stream kind of pushes it to the southeast, usually breaks it off from the Northwest Territories or from northwestern Canada, and it kind of moves southeast in the northern hemisphere down into the United States. It brings cold polar air south, displacing warmer air. And when you generally hear of a cold outbreak, it is a migratory high pressure system moving south. It's also referred to in meteorology as a baroclinic high pressure, Baroclinic meaning that we have some sort of temperature change from, for example, colder air displacing that warmer air. All right, one of the biggest things I could say when you talk about a migratory high pressure system, this cold core high, in the wintertime too, you'll just notice just an amazing blue, clear blue, crystal clear blue sky when this high pressure system moves in. The air mass is very, very clean, very crisp, it's very dry as well. Let's turn our attention now to the low pressure. Now, what is a low pressure? It's simply an area that's surrounded by higher pressure. And in the northern hemisphere, the winds are going to flow counterclockwise around low pressure. And this is referred to as cyclonic flow. And you can see it right here in the upper right. This L represents your low pressure, and you see these arrows represent the wind directions around low pressure. And so you kind of see how the winds flow counterclockwise around low pressure in the northern hemisphere. So the west side of low pressure, I'm generally going to have northwest and northerly winds. South of the south of the low pressure, we're going to have generally a west or southwest wind. On the front side of low pressure to the east, we're going to have more of the easterly winds, southerly winds, and then eventually as we get to the northeast side of the low pressure, the winds are going to be from the northeast. So wind flows counterclockwise around low pressure. The wind is also going to flow inward towards the center of low pressure, resulting in low-level converging air. And in a lot of cases, low pressure is responsible for giving us our stormy conditions as that low-level air kind of meets and the air rises in the vertical. So you have low pressure on the surface weather charts, and it's going to be denoted as a red L. So you see the red L on a surface weather chart, that is going to be low pressure. Look over here on the bottom right. I just wanted to show you briefly. It's almost like looking at a bowl. You have a troughing situation here, low pressure. So it's like a bowl. High pressure is like upside down bowl, and low pressure is like a bowl where you have a trough in a bowl. Now, low pressure, the mid-latitude cyclone, we're very familiar with this type of low pressure, specifically in the fall through the spring. The mid-latitude cyclones tend to be most intense during the winter season when you get a lot of strong temperature difference across latitudes. Low pressure is responsible for most of the active weather we experience in the United States. Again, the storminess that we get. Think of low pressure. The upper level divergence now. So we have a reverse of what we saw with high pressure. So with low pressure, we have upper level divergence up here. See this image here on the right. So the air is spreading apart higher above the surface. And then below that, because, let me go ahead and draw this out for you here. Let me go back to this. Here we go. Okay, so the air is converging right here in the low levels at the surface. See how these arrows are meeting right here? Okay. As the air converges in the low levels of the atmosphere, it's going to rise up vertically like this. And then aloft, you're going to get what's known as upper level divergence, where the mass is being moved aloft. The faster this upper level divergence occurs, or let's say the upper level divergence exceeds the low level convergence, it's going to result in a deepening or an intensification of the low pressure at the surface. And this is known as the chimney effect, by the way. Ever light a fire in the wintertime and the heat's going to rise through your chimney, just like I'm showing you here. And then when it gets up above, outside the chimney, it's going to kind of spread apart on the top. So we call it the chimney effect. So big thing is here with low pressure again is when upper level divergence is stronger than the low level convergence, you're going to get a lot of upward vertical motion here. Let me find my pointer here. My goodness, I lost it for a minute. You're going to get a lot of upward vertical motion here. As this air rises, it cools, condenses, and forms clouds, and a lot of times precipitation will fall from those clouds in association with low pressure. But in general, if you get this upper level divergence to exceed or be stronger than this low level converging air, you're going to have an intensifying storm system. Okay, so you get upward vertical motion again, surface pressure falls. Whenever the air is rising away from the surface, the barometric pressure at the surface is going to fall or lower, and the upper level height falls will also occur due to adiabatic cooling. All right, so now let's examine the low pressure types. We have a warm core low pressure, a cold core low pressure, semi-permanent low pressure, and migratory. They're identical types, similar to the high pressure we just examined. So let's take a look at these types of low pressures. You get a warm core low pressure system. Again, warm core means that the warmest temperatures are at the center of this low pressure. And many times when you get really intense surface heating, specifically in the desert Southwest, or let's say in the San Joaquin Valley, Death Valley, that area of California, in the summertime, it's usually we call it a thermal or a heat low. The low is just generally stationary. It remains over the most intensely heated surfaces. During the summer months, intense surface heating by the sun causes this air to rise. Heating is going to basically lower or decrease the air density enough for a shallow low pressure to form. And you'll see it denoted on the surface weather charts. Just look over towards the Palm Springs area, the Death Valley area, the desert Southwest. Again, you're going to get low pressure generally above those very intensely heated surfaces during the summer. These thermal or heat lows are associated with fair weather, believe it or not. The air is just so dry in that part of the country, specifically the desert Southwest. I mean, we're talking desert, right? I mean, it's very dry. So, even though the air is rising, in a lot of cases, you just get fair weather, some scattered clouds, and that'd probably be about it. And another warm core low type is a tropical cyclone, by the way. So in addition to this heat or thermal low in the desert Southwest in the summer, we have another type of warm core low, and that's a tropical cyclone. Here's an example on the right of a thermal or heat low. By the way, this object here in the upper right is actually the sun. It's going to be sending its shortwave radiation to the surface, and then you're going to have intensely heated surface. So we're talking 100 degree plus daily high temperatures over this part of the United States in the desert Southwest during the summertime, specifically right now in July. And so you're going to get you get this thermal low to show up, this heat low, and you get rising air motion. Intense surface heating causes that upward vertical motion or that rising air motion. One other thing to mention about the thermal or heat low is it's a very shallow system. Looking at a cold core low pressure now, this type of system, this is one where we'll see this one quite frequently in the winter and springtime. It extends to great vertical heights. Now look at this diagram on the left. You can clearly see we have low pressure at the surface here, and then we have lower heights or a little bit of upper low reflection above the surface low. And then we have, these bowl shapes going all the way up, extend to great vertical heights in the atmosphere. This is what cold core low pressure systems do. They usually deepen or get more intense with height. And whenever you see a mid-latitude storm system or a cyclone dissipate, it's usually going to weaken from the surface first. It's going to weaken at the surface first. It's going to weaken from the surface, and then the last reflection of this surface low pressure will be a upper level low aloft, this cold core upper level low. With significant upper vertical motion with the cold core low and moisture available, you get clouds to form. In a lot of cases, it'll be showery precip beneath the cold core low pressure. In some cases, depending on the time of year, you get a cold core upper level low moving overhead. You get an unstable situation. You actually get some thunder showers. It is associated with poor weather because of the showery precip and the clouds, and it's also referred to as something known as barotropic. Barotropic in meteorology basically means there's no air mass changes. Next up is a semi-permanent low pressure, and in this case remember what I mentioned we talked about high pressure, the semi-permanent highs. Semi-permanent meaning that it generally remains the same latitude throughout the year. It might migrate slightly, but it's not going to deviate a whole bunch. And we have two subpolar lows, specifically in the northern hemisphere, that are semi-permanent low pressure systems. We have the Icelandic low, which covers Iceland and southern Greenland. We have the Aleutian low, which sits off the Aleutian Islands near the coast of Alaska. Both of these become weak and diffuse during the summer months. Anytime we talk about low pressure, it's really going to derive its energy from temperature contrast or temperature differences. So in the summertime, there's not much temperature contrast between the water and the nearby land. Okay. But in the wintertime, these type of semi-permanent low pressure systems, the Icelandic low and the Aleutian low, really, really get more intense because you get a colder landmass next to a relatively warmer water surface, and that's going to really give these systems a lot of energy in the winter. Again, they remain in the same general location throughout the year. And finally, migratory low pressure. This is usually associated with frontal systems, gradually transitioning to the cold core upper low I just briefly talked about 2 slides ago. These migratory low pressure systems are going to be steered by the upper level winds, specifically the jet stream is going to kind of direct which way they go. It is associated with poor weather. Clouds and precipitation are very likely, specifically in the wintertime. We see this a lot. And if you look at the graphic here on the right, look at how the upper level features, okay, the upper low, how everything stacks back to the colder air aloft with height, okay? So here's your surface low, okay, with its frontal systems. You have a cold front coming out of the surface low pressure. You got a warm front coming out, extending to the northeast of it, okay? You got air mass changes, so this is a baroclinic type of system, okay? And then aloft, but I mean, let's just say this is 5,000 feet, this is 10,000 feet, and this top bowl-looking shape is 18,000 feet. Notice how this system stacks back with height in the vertical towards colder air. Once the upper low is vertically stacked, so once this is absolutely vertically, basically straight over the top of the surface low, cyclonic circulation will remain in the upper levels only. This surface system will weaken. You're basically cutting off the upper level divergence when this thing becomes vertically stacked. All right, that wraps up my training topic on pressure systems. These pressure systems affect the weather in the United States and across any of the mid latitudes. Europe, doesn't matter. If you're in the mid latitudes, your area typically will be visited by low and high pressure systems. You get more frequent passage of low pressure systems, specifically in the wintertime. And you'll have very strong pressure differences between the center of low pressures and these centers of high pressures. And that difference between those pressure systems is going to create the wind that we feel. But anyway, that's all I got for now. I'm hoping you're enjoying the training video series here at Spot On Weather. Pressure systems, I've got a lot more interesting topics to cover in the training video series. The next topic, I'm going to talk about phase changes, water vapor, liquid water, and ice. How do these phase changes occur in the atmosphere, and what is the importance in our weather? That's all I got for now, everybody. Appreciate you subscribing to the Spot On Weather YouTube channel. Until next time, everybody, take care and God bless everyone.